What I'm going to talk to you about today is the language C and C++, and overall what it is to be a programmer, what we're trying to do, how it works, this whole building programs and programming in general thing. Let me introduce myself. My name is Charlie West. I'm a graduate student here at NC State and also a full-time software developer at Primal Space Systems. Cool thing about programming. At its core, what you're doing is you're managing these really complex systems, and you're taking these really complex ideas and you're making them happen in the real world. You're literally taking them out of your head and through a very complex and arcane process, making it something that happens. You're expressing that idea and you're making it so, oh, I think that this should happen this particular way, and it does, which is cool. So, how we do that is by taking these ideas, figuring out, breaking them into components, breaking them into simpler components, and so on until we get to some sort of level of complexity where computers can actually work with it, which is really, really powerful because computers are cheap and they're really, really good at doing simple things. So, here's our problem, sort of thought experiment to get into the mindset of how this whole programming thing works. Let's say you're stuck in a room next to a kitchen. You don't know how you got there, you just woke up one day and, I'm in a room next to a kitchen. You can't escape. And you're told there's some speaker thing that says, you may not leave this room until a souffle has been made in the kitchen. Kind of a weird scenario, but hey, stranger things have happened in the world. So, you can look stuff up, there's this nice internet thing, it doesn't let you communicate out, help, I've been trapped in a room next to a kitchen and forced to make a souffle. But it will let you look up stuff like souffle recipes, because hey, handy. Thing is, and what's the only ray of hope in this situation is, there's someone in the other room, and they're willing to help you. They have some patience and understanding, and you can tell them what to do, and hopefully, at the end, you can make that souffle and escape. So, imagining this thought experiment, what would you have to say to the person in the other room to get that souffle made so you can get out of that room? Well, that depends on who you're talking to. A lot. So, if you're talking to a chef, you say, could you make a souffle, please? And that's about all you have to say, because hey, a really good chef knows how to make a souffle. You don't have to tell them anything. Just say, oh yes, I'd like a souffle, please, and it gets made. However, if it's not an expert chef, if it's not someone that already knows everything about the souffle creation process, instead, you have something that looks more like this, where you're saying, okay, ingredient 1 is sugar, then you need bittersweet chocolate, and large egg yolks, and egg whites, and all this stuff. So, you're familiar with these ideas of ingredients, so go ahead and get all those ingredients together, and then preheat the oven. You know how to turn an oven on, most people do. So you have this list of instructions. Now one thing that is really important and that you'll notice here is there's a lot longer instruction list here. Like when you're telling that chef that already knew how everything works, you just had to say, make a souffle. It was literally one sentence. With someone that isn't a souffle making expert, you have to list out a lot more stuff and break it down into ideas that they can actually work with and understand, like turning on an oven and mixing things together. That's a level of abstraction that they're able to deal with. Well, let's say if it's not a person. What if it's a robot? Well, I mean, you have the same general instructions as with a human, but to get that first step happening, it's a lot more involved. So step 1 was turning on the oven, right? Preheating it? Well, for a robot, the instructions are more like, okay, move your base 5.23 meters to the left, and then turn 92.1 degrees clockwise, and then we want it to extend the arm and then turn the thing to get that oven on. Because the robot intrinsically both knows nothing about souffles, but also knows absolutely nothing about turning an oven on. So we have to break down our idea of making a souffle into much lower level concepts that it can actually carry out, like moving and then turning and that sort of thing. Does that make sense? Okay, cool. So, the general overriding principle that we have here is, the more the person you're talking to, or the machine you're talking to knows, the less you have to tell them to get the job done. Makes sense, doesn't it? there's this whole thing in information theory where information is the amount you have to tell the other person, and that applies very closely to this idea of escaping the souffle room. So, what does this have to do with C++? I mean, souffles are fun, weird thought experiments, they can be cool, but C++. At the base level, all computers know is math and very basic logic. In fact, at the really base level, all they know is, I'm a transistor. What we're doing is we're embedding this knowledge into the computer so that it can handle more and more complex instructions, and also breaking our ideas down until we can get the idea into this list of lower level instructions, until the amount that the computer is able to do just natively, and the complexity of our deal meet in the middle, and all of a sudden, hey, we can actually build that. Because, I mean, programming is essentially where the rising knowledge of the computer meets the falling complexity of the idea, and when those meet in the middle, you can make something real. So, that's basically what it says on this slide, just put another way. So, what do computers know out of the box? Well, there's this idea of RAM. Raise your hand if you've heard of RAM. Okay, cool. Raise your hand if you know it in more detail than it's something my computer has. Okay, a little bit. So you can think of RAM when you're programming as the space where both your program's loaded and where it's going to be working with numbers and stuff. So at its core, all RAM is this really, oops, that didn't do anything. I retract that statement. It did do something. So, at its core, all RAM is basically this one long list of ones and zeros. You can think of it as just this one-dimensional string of text that's either restricted to either being ones or zeros. It's just this really ridiculously long string of text. And what any given... I'm just going to stop pressing that button completely. What any given piece of that text, been ahead a bit. What any given piece of this text, apparently if you use the laser pointer, it exits the slideshow. This is new to me. So I'm going to point and gesture frantically. Alright, pointing and gesturing frantically. This is ones and zeros. Intrinsically, it doesn't mean anything besides I'm a 1 and I'm a 0. However, what we can do is we can say, hey computer, you know this 1 and 0 at the 0th position, the sort of first position in memory? I think you should think of that as text. And if it's text, it means something. Interpret that as text. And if I want to have like a number, then that might be like 4 bytes, so it's 0. So I say, okay computer, consider there to be a number at position 0. So this byte, this byte, this byte, and that byte make a 4-byte number, and you interpret that as a number and it has some sort of value. But at its core, all it is ones and zeros, and what it actually turns into in terms of meaning that we assign it is entirely determined by what we decide to interpret that section of memory in. Which is why people say, at the core it's ones and zeros, but you see it doing all these crazy ridiculous things that aren't ones and zeros. This is how. You say, this section of memory means XYZ thing, interpret it as that. So, examples of what that means. At the top we have binary, which I will not point to with a laser pointer. 4 bytes. If you interpret it as a signed integer, it is that number. If you interpret it as an unsigned integer, since it's not negative, it is also that number. And you could also interpret it as a double, which is like a floating point number, which represents something that can have like fractions and that sort of thing. Or you can interpret it as 4 characters of text, because each text is like 8 of these little binary digits, and which would be kind of a misspelled hello, which guess how the data was generated originally. So, with that, let's move on to the actual language. So we had this idea of this really long string of memory and interpreting things as different stuff. when you're declaring variables, which are basically sections in memory in your program, what it does is say, okay, I have this pointer that is like the current place that I stick new stuff. And at the start of your program, it's like section 0. Each time you declare something in a line, it'll say, okay, well, I'm making a 8-bit integer, signed integer. So this 8 byte, or 8 bits, is going to be a signed integer. So the next thing I allocate, I'm going to stick to the next address. I'm going to move over a little bit and stick it in a different place. Raise your hand if that makes sense. Okay, cool. So if I make 8 bits there, 8-bit signed integer, it goes, okay, 0 spot, you're an 8-bit signed integer. For the next thing, I'm going to move over 8 bits, so I'm not overwriting what I just wrote. And I'm going to make a 32-bit integer. That's 4 bytes, because a byte is 8 bits. So, bloop, bloop, bloop. This is an integer, and I'm not going to write over it. So the next thing I assign is going to be a little bit further along in memory, which is great. But if you allocate too much stuff, you can actually run into, oh crap, I don't have any more memory, and then bad things happen. But in general, you have lots and lots of memory, so you just declare this stuff, and it says, this takes X amount of memory, so stick it there, and then when it goes out of scope or you stop using it, you can go bloop, 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 and get rid of that memory at the end. So, fundamental types that the computer knows about. In C++, we have, well, in most languages, we have a few different fundamental types that you'll find just about everywhere. One of them is an integer. Raise your hand if you know what integer is. Cool. I won't explain what an integer is. The only difference between this integer and any integer that you deal with in math is that it has a finite precision. It can only represent values that are so big or so small. So it's kind of this crazy exponential as you add more bits to a particular integer. So with an 8-bit integer, it can only go up to, if it's unsigned, it can go from 0 to 255. And if it's signed, then it can go from negative 127 to, I think it's 128? I could be reversing which one's the 127 and which one's the 128. But you get the general idea. It has this limited finite range. But if you make it a 16-bit integer, then it can go up to like 32 million, depending on. So, and if you make it a 32, it goes way bigger. And if you go 64, then you could be counting 1, 2, 3, 4, 5 to the heat death of the universe, and you might not get to the end. It blows up in terms of how big of the numbers you can store. But you have these different sizes of integers, but they're still integers. The only restriction is they can only get so big or so small, or else you'll have problems. So, moving on, sometimes we want to represent a half, or a third, or 2000 blah 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 0.5. This is what we use floating point numbers for, and they're exactly the same as integers in that they have a certain representable range. The only big difference is they have a limited number of precision. So you can have 10 to the 10th, and it'll store that just fine. Or you can have these other numbers, and it'll store it as x being significant digits, and then an exponent. It's got this many zeros behind it. So it's like, we have this fixed precision thing, point blah 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 blah, and then times 10 to the such and such number. Does that make sense? Okay. So, the float is a really low precision version of this. It uses about half the memory of the double one, which is why a double is called a double. It's not super intuitive that a floating point number is called a double, but it works. Mostly when we're doing normal programming, we use doubles. Floats are good in some specific applications like graphics, but they're mostly a legacy of when we did things back in the day and we didn't have nice, large-scale computer processors. So, moving on in terms of data types, things that the computer in the language has right out of the box. So we talked about in memory having this line here of the raw memory. Well, if we can declare something like a character, which is 8 bits, then if we stick it in this space, that's one character. We could declare another character, and another character, another character, another character, but sometimes we want to operate on like sets of characters. So the idea is we have a data structure called an array. Like right here, this is char for character, which is a 1-byte thing. And we have the variable name, and then how many chars are supposed to be in this variable. So what that's doing is rather than allocating just one character, or one integer or so on when we declare an array, Instead, it's saying, I want 10 of these. So 1, 2, 3, 4, 5, 6, 7, blah, 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 to 10. And it allocates that whole chunk of memory, and then later on you can actually access that using a specific operator we'll get to later. Last but not least, everyone talks about logic with computers. There is a specific value in C++ called a bool. What the bool stores is true or false. You could literally represent with just one bit. But it allows you to do logical operations, so you can set it equal to true or you can set it equal to false. But we'll get into that more in a little bit. So moving on, there's another type of thing you can do. We talked about the array, how it's stuff in memory. And we talked about how as you allocate more stuff, it moves and sticks them right next to each other as it moves over to not overwrite things. So there's also something in C specifically, and a different version in C++, called a struct. And a struct is nothing but the idea of grouping a set of different types of variables together and giving them names, so that when I make one of them, it makes all of them. So my Bob struct is made out of 2 integers, and when I make a Bob struct by saying type Bob, name my Bob struct, it allocates memory for 2 integers, and then I can access it using Bob struct dot number of pawns, Bob struct dot number of knights. Does this make sense? Okay, cool. So, we've allocated these things in memory. This is something that we can do out of the box with the language. Well, that's well and dandy, but we're allocating that memory that has mostly random junk in it, so that's not particularly useful. Well, there's an operation you can do called assignment. It's a little bit different from the math equals operations. In math, when you say something equals such and such, you're trying to prove something, or you're saying, this is the actual value that we finally derived. In programming, it's a little bit different. When you do super awesome number equals 42, previously, at that top statement, super awesome number has a completely random value in it. But after the super awesome number equals 42 statement, that statement becomes true in that you take 42 and you stick it in that memory. You change the memory value that we're referencing with super awesome number with the value 42 as a int32 type. So 32-bit integer. Does that make sense? Yes? Yes, it physically becomes 42 in memory. You take the actual bits that represent 42 as this integer 32 type thing, and you copy it, and then stick it where that memory resides, in that long string of ones and zeros. Same with doubles. If you want to do a floating point, you go, hey, I'm going to make this negative 64.0. It could be negative 64.05. And that's how you assign a floating point number. It literally takes that chunk of memory and copies it over to where that variable lives, using this C style or C++ style equals operation. So before I move on, does that make sense? Okay, cool. So, the other thing you can do is math. Like I said, computers are good at math. We have processor instructors to say, number, atom, give me the result. So we can do the same thing. We can do mathematical operations like 4 plus 4, or 3 minus 2 times 7. And it has the exact order of operations you get with normal middle school, high school math. Even elementary or something. We also have this weird operator here, where it's 14% sign 4. That's not something you see in your math textbooks all that much. But basically, what that operation does is take a remainder. So, we take 14 and we divide by 4. The most we can subtract from it before we start getting fractions is 12. So 14 divided by 4, the remainder would be 2. And that's what is stored in that fourth number. Does that make sense? Yes? It is doing modulus on a calculator, yes. In fact, that is probably internally exactly what your calculator is doing, depending on the language it's in. So, we can also do logical operations, which is very useful for doing large-scale stuff and just logical stuff. So, I have this super number, it's number 5. I can set this Boolean value equal to is super number equals 5, which is the C++ and C way of saying are these two things equal? If so, return true, and if not, return false. So right now, supernumber does equal 5, so I really hope this is true. So we're happy and stuff. We also hope that 5 is greater than 4. We're all familiar with these operators from math. It just stores the result of that operation in this variable, and you can do other operations on it. We also have less than equals to 5. That's how we write out, because hey, keyboard doesn't have the fancy math symbol where you stick the and then underneath. It's just not there, so programmers make do. So, you can also do logic to do things. So this is an if statement, and it looks a little bit weird, but at the top we have if, and then this logical value. If the calculated number is greater than 5, which could be the result of a whole bunch of other calculations, if that's true, that evaluates to a variable, a Boolean variable that's actually true, then do this thing, fires the missiles. This is what it does. It does some operation that's calling a function. We haven't gotten into functions yet. We may or may not have time. But if it's not greater than 5, if it's 5 itself, or 4, or 0, or -1 or something, it will instead make cake. So, greater than 5, do this. Not greater than 5, do that. It's called a branch operation, where you go do one thing if it's something's in a particular state, and do something else if it's different. So think of it like a flowchart. You can branch off, or don't think of it as a flowchart if you're not comfortable with that. So, the last thing, since we're running out of time, I want to talk about, well, we'll see how fast I can talk. Here's a for loop. It combines several of these ideas together. It allows you to do things more than one time. So at the top, we're declaring an integer in this for loop, kind of weird semantics. We say for, and then we're declaring an integer, saying it equal to 0. So at the beginning of all of this, the integer I is equal to 0. And then the next thing you do in a for loop is say some logical thing. So in this case, we're checking, is I less than 5? Sweet, it works. If so, then if that evaluates to true, then do the thing inside the brackets. In this case, make a cake. And then at the end of it, you have this weird I++ thing. What does that do? It takes I, it adds 1 to it, and then it returns that value. Or actually, post-increment, it actually returns the value, and then, anyway. Basically, it adds 1 to I. So what happens in this loop is, I equals 0. We check that. It's less than 5. Make a cake. Add 1 to I. I equals 1. 1 is less than 5. Make a cake. And that keeps going until, all of a sudden, I equals 5, and then I isn't less than 5, so we stop. And the end result is, we make a cake 5 times. Handy. So, I'm not going to get into this because we're running out of time. Moving on. So, we talked before about layers of abstraction, where you encode knowledge from the language and bring it up so they can do more things, so you can eventually get to the make souffle level, and it just doesn't. This is part of how you do it in a language called C and also C++. You can define a function that you can call, and it does a whole bunch of code in the middle, and then gives you the result, or just does a whole bunch of things, including making a souffle. So in this case, we have a number coming in, input number to multiply, and it's giving a number out, this integer 32. And what's returning is this operation, integer number to multiply times 100. And so if we're using that in practice, we have integer 32, 200 equals, call this function, multiply by 100, 20. And it gives you back the result, 20 times 100, which is 2000. So you can make more and more complex functions that call other functions, and this allows you to build up what the computer can do by itself until you can eventually reach these high levels of complexity where you can actually say, oh, I want to pull in this library that has all this cool stuff for networking or displaying things or computer games. And then rather than having to work with ones and zeros or this low-level arithmetic, instead you can work with place 3D actor that's going to shoot at people here, and go from there at a higher level extraction. So I think I'm about out of time, so I'm sorry, but I don't think we're going to get to classes. It's another sort of abstraction thing, and that's pretty much it. In summary, programming is a fascinating subject that you can do lots and lots of stuff that other people can't do because, hey, this is an interesting sort of magical process where you can build things that change how the world operates. And I've been doing C and C++ since high school, so going on 10 years. You can really go far. There's still lots and lots of stuff I haven't yet learned, but interested in. So thanks, and on to the next talk.